Hello again, I'm Chuck West. Welcome to the Craps Strategy Project. In the previous video in this series, I talked about how it can be difficult to evaluate craps strategies you might want to play. And then we examined two well-known strategies for their statistical characteristics. In this video, we'll look at another two popular strategies and see how they compare to each other and to the two we've already seen. This time we'll look at Double Tap and Triple Lux in detail. So if you'd like to see how those two strategies compare when simulated with 1 million shooters, stay tuned. In this video, we'll be looking at the Double Tap and Triple Lux strategies. In each case, we'll take a short look at how the strategy works, and then we'll look at the way they perform when modeled with a computer. I use custom computer programs that implement the strategies. Shooters are simulated in groups of 25 because that seems like a reasonable session at a craps table. I then run 40,000 realizations of the groups of 25 shooters. That equals 1 million total shooters for each strategy. Our first strategy for this video will be the Double Tap. It's one of the favorite strategies of David over at Casino Quest. It was also demonstrated by Jeremy at Color Up. I'll do a quick description here, but links to the Color Up and Casino Quest videos are included in the description below, and those will give you a more complete picture of how to play each strategy. For Double Tap, you don't need a pass line bet unless you want to be the shooter. If you are, you can modify the bets to include the pass line bet and the odds, but here we'll assume you're not the shooter. Once a point is established, you place your bets in $10 increments on the 5, 6, 8, and 9. That's $10 on the 5 and 9, and $12 on the 6 and 8. The first hit on any of your numbers pays $14. You use the winnings plus an extra $1 or $4 to power press the numbers. If the number is a 5 or 9, you add $1 to power press to 25. If it's a 6 or 8, you'll add $4 and press to $30. Now, other numbers may hit, and you power press them too, but you are really waiting for that second hit on any pressed number. The second hit on a pressed number will pay $35. If you collect those winnings, as well as regress the power press number back to its original bet, you'll have either $50 or $53, depending on whether it's the 5 or 9 or 6 or 8. If you subtract the money you used to power press plus the original 44 inside, you're left with $5 profit, and all your bets are paid for. From there, you can press and collect, or expand to the 4 and 10, or just collect, or really do whatever you want. So now you've seen how the strategy works, we can take a look at how it performs in some simulations. The simulations are based on computer programs that run the strategy I just described for 1 million shooters. We'll look at the results with a couple of different kinds of graphs that aggregate the results. I know graphs can sometimes be a little intimidating, but I'll do my best to explain them and point to the important results along the way. This is the first plot we'll look at. It's called a histogram. It's in its bare form right now, so I can explain it. I'll add some reference lines to it in a minute. First, the bottom axis is the number of bets won per 25 shooters. From 0 to the right, the numbers are positive, indicating winnings. To the left of the 0 are negative numbers, indicating losses. Internally, the program works in bets, but just consider a bet to be $10, so you can multiply the numbers on the horizontal axis by $10. The vertical axis on the left is the number of times that a particular result happened in the 40,000 groups of 25 shooters. For instance, this bar here represents somewhere between 0 and 50 bets won, about 20 or 25 or $200 or $250. And it happened almost 800 times in the 40,000 simulations. It's really that simple. What's important is the distribution of the results. So let's look at that. Here I've added a little bit of statistical information on the plot. One important thing is the mean or average of the distribution. The mean is shown here by the red line and is about -7 bets, or -$70 per 25 shooters. So if you played the double tap strategy for a very long time, you'd lose a little less than $3 per shooter on average. Since the median is close to the mean, and we'll talk about the difference a little later in the video, we can say that half of the time you'll do better than that, and half the time you'll do worse. As usual, keep in mind that no strategy is going to have a mean that's greater than 0. The casino makes sure of that. But there are plenty of times where you can make money. All of the results inside this triangle represent winning groups of 25 shooters. It's just that this red box, which holds the losing groups, contains more total losses than the winning groups contain winnings. That's why the mean is less than 0 and why the casino stays in business. Now let's look at the data in another way. This plot is called a heat map. It shows the outcome of each of the 1 million shooters in terms of the length of the roll and the bets won. On the horizontal axis here is the length of the roll. This includes the 7 that terminates the roll. So here, for instance, is a 0.7 out. It's a roll of length 2. There's no roll of length 1 because there's no such thing. You'll always have a second roll if you want one. On the vertical axis here is the number of bets won. Everything above 0 bets is a profit, and below 0 is a loss. So let's say we have a roll that goes on for 15 rolls and wins 10 bets. We'd go up from the 15 and over from the 10 to one specific point on the plot. Now let's say we plot a pixel of light at that spot on the plot. And then each time one of our 1 million simulations is 15 rolls long and wins 10 bets, we make a pixel of light a little brighter. If we do that for all of the rolls and all of the pixels, this plot is the result. The brightest points are the white ones in the lower left. They happen the most often. The dim ones in the upper right rarely happen, and the black ones in the upper left and lower right never happen. The blue-green dots are the average number of bets won for each roll length. For instance, this dot is the average of winnings up here and the losses down here. This gap here happens because the strategy has you reinvest any winnings into your bets until you make that double tap. And then you regress to break even or a small profit. Your entire initial investment is at risk until you get that second hit. The averages fall in between because that second hit can come at any different time during the roll, and that time becomes more and more likely as the length of the roll increases. But this plot is slightly misleading because it includes come-out rolls where you can't make that second hit and your bets aren't at risk. So let's take a look at the plot in a slightly different way. Here, all of the come-out rolls have been removed, and only rolls where your bets are at risk have been included. Note that now there is a roll of length 1. That's still a 0.7 out, but the roll where the point was established has been removed. Overall, you can see that it takes about 7 rolls, excluding come-out rolls, to get to break even. Now, I said that this plot contains all of the 1 million shooters that were simulated for the strategy, but astute observers will have noticed that the data clearly extend beyond the upper right boundaries of the plot. That's true. There are some shooters out there, but it's less than 1/10 of 1% of all shooters. At-risk rolls of length 40 or longer are just extremely rare. Now that we've had a look at the double tap, we can move on and compare it to Triple Lux. Triple Lux is a very popular strategy to come out of Casino Quest. I'll link to the video in the description below. Jeremy at Color Up also covered the strategy, so I'll link to his video as well. It's a kind of wild strategy that has you power pressing like the double tap, but it has you press twice before you collect, and then you continue that process of power pressing twice and collecting once. I'll go over the strategy a little bit next. Obviously, when it works, it pays off big. But how often does it work? Our statistics will give us some idea. For Triple Lux, you wait for the point to be set. You don't have to bet on the pass line unless you want to be the shooter. The setup for Triple Lux is simple. It has you making bets in $15 units on everything but the point. That's $15 on the 4, 5, 9, and 10, and $18 on the 6 and 8. So the initial investment is either $78 or $81, depending on where the point is. The important thing about Triple Lux is the bet progression. So let's look at how that works for the different box numbers. For the 6 and 8, you start with bets of $18. The first hit pays $21. To that, you add $3 from your bankroll. You add the $21 winnings and the $3 from your bankroll to the original bet to get a new bet of $42. The next hit will then pay $49. Combining that $49 with your original $42 gives you a $90 bet and $1 back to your bankroll. At that point, the third hit on the same number would pay $105, which you collect. That $105 pays for your original $78 or $81 investment, plus any small amounts used to power press the numbers. Now let's look at how the bets progress on the 5 and 9. For the 5 and 9, you start with bets of $15. The first hit pays $21. You add the $21 winnings to your original bet, taking $1 back to your bankroll, to get a new bet of $35. The second hit on that number will pay $49. Combining that $49 with your original $35 and $1 from your bankroll gives you an $85 bet. At that point, the third hit on the same number will pay $119, which you collect. Like the 6 and 8, that $119 pays for your original $78 or $81 investment, plus any small amounts used to power press the numbers. Finally, let's look at how the bets progress on the 4 and 10. For the 4 and 10, you again start with bets of $15. The first hit pays $27, or possibly $29, depending on the casino, but it doesn't really matter. You add $25 of the winnings to your original bet, taking either $2 or $4 back to your bankroll to get a new bet of $40. The second hit on that number will pay $78 after a $2 VIG. You could just collect that $78, and that would pay for the hand. but the Triple Lux has you continue on. With the $78 winnings and your original bet, you can create a $100 bet, taking $18 back to your bankroll. The third hit pays $200 after you pay a $5 VIG. As with the other numbers, that $200 pays for your original investment, but here there's a little more profit. Triple Lux requires 3 hits on the same number to collect. You make a small initial profit, but it does leave very good bets on the table for continuing on with the roll. So obviously the strategy is intended for very long rolls. There are a second and third level of Triple Lux bets where you continue to power press twice and then collect once. The question is, what are the chances of 3 hits before a 7 out? As usual, we look at the statistics of this strategy by running simulations of 1 million shooters. This is the type of plot we saw earlier for the double tap and other strategies. It's called a histogram. As before, the horizontal axis represents the positive and negative bets won, representing winnings and losses. On the vertical axis, we represent the number of times a particular result occurred in the 40,000 simulations of 25 shooters each. But there are some major differences from the earlier plots. To make the differences easier to see, I'm going to put this plot side by side with the same plot from double tap that we looked at earlier. Here we have the plot for Triple Lux on the left and double tap on the right. First, notice that the mean or average net return for double tap is about -7 bets, but the mean for Triple Lux is -23 bets per 25 shooters, or 3 times as much. That translates to a loss of about 1 bet, or $10 per shooter. But if we look at the median values, we have a different story. The median is the value which half of the observations are greater than and half of the values are less than. For double tap, the median is about -9 bets. But for Triple Lux, it is -73 bets. So far in this series, our medians have been close enough to their respective means to avoid talking about them. But with Triple Lux, we need to discuss it. We'll get back to that in a minute, but first let's talk about these plots a little more. The next thing to notice is that the horizontal scale is very different between the two plots. Double tap contains most of its distribution within about 150 bets. The plot for Triple Lux extends all the way to 2,500. That's because when I ran the program for double tap, I just followed a simple collect strategy after the double tap part executed. But for Triple Lux, the bets continued to increase to the second level and generate very large returns. Next, notice that the shape of the distributions is different. While the distribution for the double tap is fairly symmetric, the distribution for Triple Lux exhibits something called skew, where the distribution trails off more heavily in one direction than in the other. We call that skew. We can see the skew statistic at the top. Double tap has a small skew value of about 0.4, but the value for Triple Lux is 3. That's much larger. This is the reason that the mean is so different from the median. So let's take a short detour to make sure we understand the mean and the median a little better. To understand the median, let's take the hypothetical case of a man living in some kind of bubble. He doesn't know what's going on outside, but he wonders what the outside temperature is. To solve his problem, he has an idea. He has 5 neighbors who are also living in bubbles, but they have thermometers attached to the outside, and he can contact them. But which one to contact, and how will he know if the value he gets is reliable? Being a good scientist, he decides to contact all 5 of them and take the average. The average, or what scientists and statisticians call the mean, is just the sum of the 5 values divided by 5. So our intrepid scientist conducts his experiment and calls his first neighbor, who reports a temperature of a chilly -1 degrees. He calls the second, who reports 0 degrees. The third reports 3 degrees, and the fourth reports -2 degrees. So far, so good. But now he contacts the 5th neighbor, and that neighbor reports a temperature of a balmy 100 degrees. Now our scientist is left with a bit of a dilemma. The 100-degree observation is what's known as an outlier. He's tempted to just throw it out and to use the other 4 values, but it's not very scientific to throw out data just because you don't like it. There's no objective reason to think that the measurement is wrong or that the instrument is broken, and there's a small possibility that the value is correct and the other 4 are wrong. Stranger things have happened. So he decides to go ahead with the experiment as planned and does the calculation. He starts with 2 degrees, adds 0, adds 3, subtracts 1, adds 100, and then divides that total by 5. That gives him 20 degrees. 20 degrees is the mean. 20 degrees is a perfectly valid statistic. It's the mean of the observations. The problem with it is that it's not very useful. It's unlikely to be the temperature our scientist will experience if he goes outside. He has 4 observations that say it will be around 0 degrees, and 1 observation that says it will be about 100 degrees. Nothing suggests that it will be 20 degrees or even close to that. What can he do? Is there a statistic that he can use that is less sensitive to outliers? One thing we can look at is the median. If we sort the data in order of increasing value and then simply select the middlemost value, that's the median. In this case, that's 0. 0 is a pretty good guess as to the temperature you would experience if you went outside. Another approach is to take what's called the mode. The mode is the most frequent value observed. Here we only have a few values and none of them repeat, so what's usually done is to place the value into bins. Let's pick bins of 5 degrees starting at 0. So our first bin is centered on 0 and goes from -2.5 degrees to +2.5 degrees. The second bin is centered on 5 degrees and goes from 2.5 degrees to 7.5 degrees, and so on up to 100 degrees. The 100-degree bin goes from 97.5 degrees to 102.5 degrees. So our 0-degree bin has 3 values in it: -2, -1, and 0 degrees. The 5-degree bin has 1 value, 3 degrees. And the 100-degree bin has 1 value in the 100 degrees. All of the other bins have 0 values in them. So our mode in this case is 0 degrees because that bin has the most values in it. Once again, a temperature of around 0 degrees is a pretty good estimate of what you would experience if you went outside. The median and the mode are both statistics that are less sensitive to outliers than the mean. They're not better or worse than the mean, they're just alternatives that might give you a better understanding of what the data are telling you. With that knowledge, we can return to the triple Lux plot. Looking again at the results for the simulations for triple Lux, we see that the mean is about -23 bets. per 25 shooters, but the median is negative 73 bets per 25 shooters. That's a big difference. The mean is being pulled up by a relatively small number of very large wins out in this region. But that's not a common experience. Those large wins don't happen very often. They don't happen very often, at least in our 40,000 simulations. This is analogous to the one temperature of 100 degrees pulling up the mean to 20 degrees, while the median stayed down at 0 degrees. The median, remember, is the middlemost value in the simulations, so it gives you an idea of your surroundings when playing. But the most common value, the mode, is about negative 100 bets. And you can see that the other results are heavily clustered around that value. Negative 100 bets per 25 shooters means, on average, $1,000 lost. That's the most common result you can expect, on average, for a group of 25 shooters. Now let's look at the strategy with the heat map. This is the same kind of heat map we saw earlier with the double tap. The horizontal axis shows the length of the roll, including the final 7, and the vertical axis shows the number of bets won. As with the double tap, I'm not showing come-out rolls. I'm only showing rolls where the bets are at risk. The blue-green dots are the average winnings at each roll length. As with double tap, there's a point on the vertical axis that represents 0 bets won. Above that line is a profit, and below it is a loss. The triple Lux strategy makes it fairly tough to recover your initial investment. In fact, for rolls up to length 3, it's not possible to recover anything at all. And you can see that it's not until a roll of length 11 that the strategy makes an on-average profit. If your initial triple hit is on the 4 or 10, which is indicated by the blob here, you have pretty good winnings. But you're much more likely to have the first triple hit on the 5, 6, 8, or 9, where the winnings are more or less just enough to get you out of the hand. But the nice thing about triple Lux is that it usually leaves you set up with good bets for continuing the roll. As you can see, the profits pick up quite dramatically as the roll extends. So for long rolls, it works very well. Now that we've had a look at the triple Lux, let's compare it with double tap and the other strategies we've looked at. Here I've added double tap and triple Lux to our table of craps strategies and highlighted them in color. Looking at the mean, you can see that double tap has the best performance of any of the strategies we've looked at so far. On the flip side, triple Lux has the worst, just a little worse than the Iron Cross. But when we look at the medians, we see that for most strategies, they're just a little worse than their means. But for triple Lux, it's much worse at minus 73 bets per 25 shooters. And earlier, we found that the mode was even worse. If we look at average number of dice rolls required to reach a profit, we see that double tap takes 1 roll longer than the earlier strategies. But triple Lux at 11 rolls takes much longer. This is one reason its performance in the earlier categories is so much worse than the other strategies. Finally, looking at the initial investment, we see that double tap only starts with 4.4 bets. That's $44 at risk. That's considerably lower than the other strategies, and is one reason that its mean in loss is so low. Triple Lux, on the other hand, requires an initial investment of around 8 bets, or $80, which is higher than the other strategies, and is another reason that its mean and median are so negative. All of this suggests that triple Lux may not be a good starting strategy. Your mileage may vary, of course, but it may make sense to start with another strategy, maybe even double tap for squeeze play, something that pays for your bets and then use Triple Lux as a continuation from there. That way you avoid Triple Lux's high initial expense at shorter rolls while taking advantage of its benefits on longer rolls. On the other hand, double tap seems like a viable starting strategy, but it needs to be followed up with a pressing strategy of some sort. That's about it for this edition of the Crap Strategy Project. I hope you found it valuable. In the next video, I'll cover 2 more well-known strategies and see if we can find their strengths and weaknesses. Let me know in the comments what strategies you're working with, and I'll try to include them in a later video. As always, thanks for watching. Until next time, may the dice roll in your favor.